Now we're going to move from quadratics into cubic functions. And as you'll notice, as we've gone down through the different types of functions, we've simply increased the degree. So we've gone through linears of degree 1, we've gone to quadratics of degree 2, and now we're going to cubic equations of degree 3. And what I mean by degree 3 is that the highest power in a cubic expression will be x cubed, or any variable cubed, but cubed will be the highest power. And I suppose most of us are familiar with a cubic function, something like this: ax cubed plus bx squared plus cx plus d. That is a cubic function, okay? And the one thing that we know about the highest power in that function is that that also tells me the number of roots, okay? Or the number of solutions. Now, just as a matter of interest, when you're drawing graphs, any time a function cuts the x-axis, that is a solution, okay? That is a root. So therefore, what I will be saying to you is this, that cubic functions in terms of the x-axis will always cut the x-axis at least once. Just think about that. Quadratic functions don't have to cut the x-axis, okay? They could be u-shaped, but the u could be above the x-axis. Linear functions will always cut the x-axis, but cubic functions must cut the x-axis once. And I'll just give you an example of that. So there's your y and your x-axis. So you could have a cubic function, something like this, which means that there's only one real solution. Now, what are the other two? There has to be three solutions. So what are the other two? Well, this one here is what we call a real solution, and the other two solutions are non-real. Now, we do have a branch of mathematics which we call imaginary mathematics, and we will come back to it. You did deal with it with me in transition here, some of you. We would have talked about complex numbers, okay? So non-real are imaginary solutions or complex solutions, okay? And that's something we'll deal about when we're doing with complex numbers later on. But I do just want you to remember that a cubic function has to make contact with the x-axis once, meaning that every cubic function has at least one real root. It may have two or three, but it will have at least one real root. Okay. So, as I told you already, ax cubed plus bx squared plus cx plus d is a cubic function. If a is positive, now this is the other thing about this function here, the coefficient, what we call the leading coefficient, and that there is the leading coefficient. That also tells me an awful lot about the shape of the graph, okay? If the leading coefficient is positive, well, that means that the start of the graph will be increasing. So, for example, if a is greater than 0, then here's what I know. The graph will be increasing before it turns to decreasing to go back to increasing again, okay? And if a happens to be less than 0, in other words, if a is negative, well, then we'll have a decreasing graph before it increases and before then it goes back down to minus infinity, okay? So just to keep in mind that the two things we really have to watch first and foremost is, first of all, x cubed, that's the number of solutions, 3, but then whether the leading coefficient is negative and positive. And the leading coefficient also has a direct influence on the height of the turning point. So I'll demonstrate that to you in a question in a moment. But it does have an effect. So if you change the value of a, you also change the heights of the turning points with relation to the x-axis. And I'll demonstrate that in a moment. So there's what we said. If you've got a being positive, you will have a graph that is what we call increasing. Don't forget, in this part of the world, we read from left to right. So therefore, you always read your graphs from left to right. Okay, so that's increasing, that's decreasing, and that's increasing again. Okay, if a is negative, well, then we get the other thing, where we get a decreasing before it's increasing and decreasing again. So just watch the value of a, the leading coefficient, at the start of your cubic function. Cubic functions, I told you already, will always have at least one real root, and I've explained that to you. Because whether it's increasing, it's going to cut the x-axis, or even if it's decreasing, it'll eventually cut the x-axis. So there'll always be at least one real root, meaning that one of the values you will be able to find, perhaps even by inspection, but we worry about that later. We did cubic expressions with the algebra, and I told you that when you were solving cubic expressions, to go to the very last term, d, and the root of this would have to be a factor of d. So the first root, if you want to put it that way, that you find by inspection would have to be a factor of d. And then we filled it in until we found a value that satisfied the function. And as long as we had a root, then we had a factor. And then by division or by comparison, we were able to find the other two. Okay, so here's a worked example. Graph the function g of x, which is x cubed minus 5x squared plus 3 of x plus 9 in the domain minus 1.5 less than or equal to x less than or equal to 4. Now, I do hope people are able to use their calculators. You can put your calculator into function mode, into table mode. And the best way to do that is just to press mode and 3, okay? And once you get that f of x, once you see that f of x, then you are ready to put your formula in. But what you've got to remember is that every time you're putting in x, x is the place in the function that's active. That's where you're going to fill in your domain values. So don't forget that you have to use what's called alpha with x, which is down above the bracket. So alpha x above the bracket down there. That's what you press every time you want to put in the x's from your function. Now, I've already done this. This is the wonders of modern technology. I've this done already. So if you were to put that into your calculator and take the domain values starting at minus 1.5, finishing at 4. Now, look, because we're starting at a half value, my suggestion would be that you would always go in steps of a half. So if you're asking the calculator to do this for you, put in minus 1.5 as your start, put in 4 as your finish, and put in steps of 0.5. So if you want to pause this video, go and do that now. Okay, so take a look at the values on your calculator. Hopefully you're able to program that properly. The table on your calculator should be the same as the table I have here. Okay, now that's quite an amount of points to plot, but you got to plot them. You got to draw this graph as carefully as you can. But that's what your table should look like. Running from minus 1.5 in half unit increments up as far as 4, and then the corresponding range values underneath y are the corresponding other halves of your coordinates. And when you plot this, as I have done, again using Desmos, you get a graph something like the following. Okay, now I'm going to ask you to go to this question. If you go to page 144, and if you open this 6.13, now it's already done in your books, but I want to run through it with you, because there's a number of things in here that I need to look at, okay? And a number of different things they may ask about this graph. And I'm going to take them one by one. So the first thing it asks me to do is to estimate. Use your graph to estimate. Now that means you're going to be drawing on your graph, okay? And estimate means there's a margin of error either side of the answer for which they'll still give you full marks. So don't be too worried about accuracy here. It's more important you know what you're doing. The values of x for which f of x equals 0. So they want to work out the values of x for which f of x is equal to 0. Now, two things here. First of all, they're asking you for the values of x. So your answers are going to come from the x-axis. And also, they're asking you for which f of x is equal to 0. F of x happens to be your range. In other words, f of x happens to be your y values. Okay? And that's equal to 0. So another name for f of x is y. So therefore, f of x equals 0 becomes y equals 0. And don't forget what y equals 0 is. Y equals 0 is the x-axis. So if you try to take this language and decipher it, I want the values of x, so my answers to come from the x-axis, where the line y equals 0 cuts the graph. Now, the line y equals 0 is the x-axis, because there's y equals 0. So you draw horizontally through that, and you get a value there. There's your first value. And then you also get something happening here. You get this coming down, touching 3, and leaving 3 again. Okay? Now remember what I told you already. There has to be 3 answers. There are 3 functions to this thing, or 3 roots to this thing. So therefore, the first root will be minus 1, and the other 2 will both be 3, because this is approaching 3 and then it's leaving 3. So if you have a graph that turns through a value on the x-axis, then that value happens to be the 2 remaining roots. So they're asking me for the values of x. What are they? X equals minus 1, x equals 3, and x equals 3. And yes, you do have to put the 3 down twice, because the graph turns at that value, which means x equals 3 and x equals 3 are the other 2 roots. So again, remember, x cubed means 3 roots. F of x equals 0 means y equals 0. Run a line through the point 0 on the y-axis, and you'll discover very quickly it's actually the x-axis. So where does the x-axis hit the graph? The answer, once at minus 1 and twice at plus 3. Okay, what's the second one? So I'm just going to do these one at a time. The second one is find the value of f of 2.5. Now, values in functions that are inside the brackets are domain values. They are x values because you put your domain value into the function. So that means that you've got a domain value here of 2.5. Another way to say that, x is equal to 2.5. Okay? Now, where is x equal to 2.5? Well, first of all, you go to the x-axis and you discover where 2.5 is. So you go to the x-axis, you locate 2.5, and what you do, to the best of your ability, is you draw a line through it, like that. Okay? And where that line, x equals 2.5, where that line cuts the graph, you then detour 90 degrees, like that, across. And what I now see is that the answer on the y-axis is just a little bit under 1. And again, I'm told to estimate, so that's perfectly fine. So I can see here, if I hit the graph and run across, because there's where I hit the graph, run across at 90 degrees, I see that the answer y is roughly about 1.85 or 1.9, roughly in that area. Now, because I'm sketching, I get full marks for that. That's no problem, but that is your answer. So your answer will always lie on the alternative axis. Here I'm starting on the x, so my answer will come from y. Okay, part 3. Find the minimum value of f of x, where x is greater than 0. Now there's two things here, okay? They want you to work out the minimum value of f of x, but this time it has to be where x is greater than 0. Now, first of all, where is x greater than 0? X is greater than 0. There's your x-axis. X is greater than 0 from there onwards. So in other words, they're asking me to focus only over here. Now take your graph between 0 and 4. Where is that graph at a minimum? Well, starting from here, the minimum value is there. It's at the turning point. So there's your minimum value. Okay? And what does it drop down to? The minimum value of f of x. Don't forget what f of x is. F of x is another name for y. So the minimum value of y where x is greater than 0. So on this part of the x-axis, the lowest value of y that I hit is 0. So the answer is y is equal to 0, is the minimum. Okay, so they're quite easy to read once you get the idea of the language behind the questions. Okay, part 4. The values of x, so again, we're reading off the x-axis, so values of x for which f of x is decreasing. Now, decreasing. I want you to think about that for a moment. The values of x for which f of x, now I normally always in my head, whenever I hear f of x, I call it y, all right? And the same goes for g of x or h of x. The name of the function is just another way to represent y. So the values of x for which y is decreasing. Well, first of all, again, as I told you, we read from left to right. So if I come in here, what am I doing until I reach to the turning point here? Am I increasing? So that's not what I'm interested in. So all of this up to the turning point about here is increasing. Now, from the turning point, which is roughly there, all the way down to here, that's where I am decreasing. Because I'm sliding downwards. I'm dropping down, see that? The y-axis. As I go from there, the turning point, down to here, my values of y are decreasing. Watch. As I go from there down, I'm decreasing. So it's asking me, what are the values of x for which y is decreasing? And the answer is, well, let's drop that down there for a start, because it's between that value and this value on the x-axis. Now, what's this value here? Well, that's 0.3. And this value here is 3. So therefore, the values of x are x equals 0.3 and x equals 3. So you can simply say that y is decreasing between x equals 0.3 and x equals 3. And as long as you show them on your graph, you'll get full marks. Okay. Part 5. The solution of x cubed minus 5x squared plus 3x plus 9 equals 2. Now, they want a solution of that. Here's the first thing I want you to notice, because it is a little easier than it looks. If you take a look at the first half of what they've just given you in the question, the left-hand side, isn't the left-hand side exactly the same as the function that I've just been using? And if they are the same, then all I have to do is to replace all of that there with f of x, or in this case g of x. Yeah. Now, g of x is another name for y. So in other words, x cubed minus 5x squared plus 3x plus 9 equals 2 becomes g of x equals 2, which eventually simply becomes y equals 2. Now, what do I do in a situation like that? I go to the y-axis and I go to the value 2, which is there, and I draw a horizontal line through it as best I can. And that line there is the line y equals 2. And wherever it cuts the x-axis, I drop perpendicularly, wherever it cuts the graph, I should say, I drop perpendicularly onto the x-axis. And I get 3 solutions. First solution is minus 0.5, 6, 7, 8. So minus 0.85. This solution here, 2.1, 2.2. And this solution here is about 3.7. So, what are the values of x for which x cubed minus 5x squared plus 3x plus 9 equals 2? Well, the answer is x equals minus 0.85, x equals 2.2, and x is equal to about 3.7. Now, I'm just going to do that again very, very quickly so you see exactly what I'm doing. Watch it again. The question says, part 5, get the solutions, and solutions, by the way, as you know at this stage, always come from the x-axis. Okay, if they want values of y, they'll ask you for the values of f of x, or g of x in this case. Okay, so x cubed minus 5x squared plus 3x plus 9 is equal to 2. Now, take a look at the left-hand side of what they're asking you. The left-hand side of what they're asking you is exactly the same as the function that we're dealing with, and the name of that function is g of x. So instead of using all of that, I'm going to replace it with g of x. But here's what I know. The name of the function is also a substitute for y. So what do I end up with? I end up with nothing more than y equals 2. So I go to the y-axis, I find out where 2 is, I draw a line horizontally using a ruler across that as best I can. Oops. You'll do this an awful lot better than me because you're going to be using a ruler. Then you immediately drop perpendiculars wherever that line crosses the graph. So as soon as it cuts the graph, you drop down onto the x-axis to get your solutions. And you'll discover here, as I told you already, that this is roughly about minus 0.85. This is roughly about 2.2. And this is roughly about 3.7. So they would be the 3 values, or the 3 solutions of x cubed minus 5x squared plus 3x plus 9 equals 2. Okay, and look at the last one. The last one is similar. It's x cubed minus 5x squared plus 3x, but then they change the last number. They say equals minus 4. Now, the first thing I want to show you is this. Let's bring that minus 4 over, because we can't solve any cubic or quadratic expressions unless they're equal to 0. That's a good rule to get into. So that becomes x cubed minus 5x squared plus 3x plus 4 is equal to 0. Now here's my question. How would I get that left-hand side to match this left-hand side? So think about that. How would I get x cubed minus 5x squared plus 3x plus 4 to match x cubed minus 5x squared plus 3x plus 9? Isn't the answer to simply add 5? So couldn't I, let me just expand this a little bit, couldn't I just add in here at the end? Where are we? Pen. Plus 5, couldn't I do that? Add 5 on that side, and then of course you'd have to add 5 on the other side. See that? You'd have to, because to keep it balanced, it was equal to 0. You've now added 5 on both sides. So in doing that, what I have done is I have allowed the left-hand side to be exactly the same as the original function, which means I can replace it with g of x is equal to 5, which basically means, because the name of every function is y equals 5. And what I do there is, again, I go to the y-axis, I find the point 5, and I draw through. Oops, like this. And every time it cuts the graph, I drop a perpendicular downwards onto the x-axis like so. And those three x values are the solutions. So x will be equal to what? About minus 0.6. This one here is about 1.65. And this one here is 4. So the three answers, 0.6, x equals 1.65, and x is equal to 4. Okay, so that's how those questions are asked. Now, most of this stuff you would have done with quadratics for your junior cert, okay? We're just taking the same type of questions, but we're now putting them on top of cubic expressions. But pure practice. Practice makes perfect with these type of questions. Okay, let's move on. Now, transformations. We have to talk about transformations because we've talked about transformations of linear equations, we've talked about transformations of cubic equations, so we're now going to talk, or of quadratics, I mean, we're now going to talk about transformations of cubic functions. Again, two things. First of all, ax cubed plus bx squared plus cx plus d is a cubic function, okay? Now, there are two things I want you to watch carefully, two transformations to look for, and here it is. If it's a case that we take that original function and put some type of number in front, well, then what we do, if we change the value of the leading coefficient, we also not only flatten the curve, but widen it somewhat. So you'll notice straight away that if I begin to interfere with this leading coefficient, I'm going to change the height of the turning points, but I'm also going to push out the graph a little bit wider, or maybe a little bit narrower, okay? So that's the first thing. And the second thing then I could do is I could take the cubic function, but what I may do then is add on another constant at the end. Now, what will that do? That will simply change the horizontal position, or sorry, vertical position, the vertical, up and down, the vertical position, all right? So the coefficient will change both the height and also the width, whereas any new coefficient or a constant being added on the end will change the vertical position of that graph. Let me just demonstrate that with an example. So let's take this one here. F of x is x cubed minus 2x squared minus 5x plus 6. So there it is. I've already drawn it. That's the one in the blue line. And then it says, sketch the following. Sketch 0.5 times the original function. Now, there's two things going to happen here. First of all of these numbers are going to be halved. So you could end up with 0.5x cubed at the beginning. And here's the key thing. Go to the end. Half of 6 is 3. Now, here's what I'm going to suggest is the easiest way to do this. If I'm asked to sketch that, because the leading coefficient is now smaller than 1, the heights of the turning points are going to be closer to the x-axis. So the heights are going to be halved. The original height here is just about 6, 7, 8, just above 8. So therefore, that's going to drop to just about 4. Okay, roughly about there. Okay. This one, turning point here, is at 4, so that's going to be halved to about there. And then the last thing we notice is that what was going through 6 is now going through 1, 2, 3, like that. So we have now, here's me turning point gone, we now have a graph that looks something like this. See that? Something similar to that. And again, I'm only told to sketch. So once I have a change in height and I'm going through the point 4, as I was already, isn't that 4? 4, 1, 2, oh no, 3. So I was right. Once it goes through the point 3 and the height is reduced by half and this height is reduced by half, well then my sketch is perfect. Okay, let's do one more. That's the first one. Second one, sketch x cubed minus 2x squared minus 5x plus 9. So now, what's happened there? Look at the original function. No change in the beginning, so the heights will be the same. The change here is that you now have a graph not going through plus 6, but going through plus 9. 5, 6, 7, 8, 9, be up here somewhere. All right. So now what you'd notice is that your turning point would also be 3 spaces above here. 1, 2, be up here somewhere. This turning point would also be 1, 2, 3 to about here. So you'd now end up with something like this. See? Where it models and it's almost parallel to the original, but it's been lifted up by 3 units, and that's been lifted up by 3 units, and that's been lifted up by 3 units. So the key thing to remember is this: if the coefficient changes, so do the heights of the turning points, and so does the width of the graph. If the last constant changes, so does the vertical position of the graph. So this one, as I told you already, that height is reduced by half, that height is reduced by half, okay? And then half of 6 is 3. So because the last constant has changed, it's going to go through that point. So you end up with something like this, as I told you already. All right, like that. And then the last one, no change in the beginning, but a change in the last constant from 6 to 9. So that means it's gone up 3 units. So that point there will go up to here, that point there will go up to here, and that point there will go up to here. Okay, so you'll end up getting something which is parallel, almost like that. Okay, and so on. Now, apologies, that's the only way I can do it on these slides, but I hope you get the idea. But they're the only 2 transformations of cubic functions that we have to watch for. So let's take a look at question 8, page 146. The graph of x cubed minus 3 is to be shifted right by 2 units and down by 3 units. What is the new functional form? Now, it's to be shifted right. That's a horizontal shift. Shifted right, okay, by 2 units, and then down by 3 units. So I want to take x cubed minus 3. I want to shift it to the right hand side by 2 and then bring it down by 3. Now, here's what you've got to remember. First of all, if you want to bring it down by 3, that means that the last constant is going to change by minus 3. So therefore, a drop of 3 would bring it down to x cubed minus 6. Okay. Now, what about the horizontal shift? We're going to the right, and the only way that I can get plus 2 out of that is by x minus 2. Okay, because x minus 2. So what I'm going to have to do there is change this x to x minus 2 cubed minus 6. And that is the new functional form of what was x cubed minus 3. So let me do it again, just very quickly. X cubed minus 3 is to be shifted right by 2 units. Now, how do we do that? To shift across by 2 units, it's x minus 2, okay? And then down by 3 units. That means that the vertical shift is down 3 units. So let's bring the minus 3 into the minus 3 first of all. That will give me x cubed minus 6. And then what was x has to be changed into x minus 2. So what was x cubed is now x minus 2 cubed. And that's the new functional form of that particular function. Okay, and I have it printed out here, I hope. Yeah. Down 3 units means minus 3 added to the end of the existing function. So minus 3 is minus 6. And finally, the value that will cause a shift by plus 2 on the x-axis is minus 2. So it becomes x minus 2. What was x cubed will become x minus 2 to be cubed. And then what was minus 3 becomes minus 6. Okay, the last example I'm going to do here now is an everyday example of using a cubic function in order to just gather information about a real world situation. Okay, and this is on page 147 by the way, not 57, 147, and it's question 13. The height in 5 centimeter units. Now, that's important. What that simply means is that every y unit is equal to 5 centimeters. So in other words, 10 on the y-axis would be 50 centimeters in real life. Okay, and we have to remember that for the graph. And the height is modeled by a function x cubed minus 7x squared minus 5x plus 75. Question, where x is time passed in seconds. Draw a suitable graph to show the height of the mosquito over the first 8 seconds. Now look, again, you do the same thing. You go to your calculator, you turn on your function, so you press your little mode button and 3, so you get your little f of x. Let me just show you there. There it is. That's what you're looking for, little f of x. You type in your function using alpha x. Now, draw a suitable graph to show the height of the mosquito over the first 8 seconds. That's from 0 to 8 on your domain. Okay, so you start at 0, you'll finish at 8, and I would suggest units of 1, no problem. So tell the calculator, start at 8, finish, start at 0, finish at 8, and take units of 1. And if you do that, your table will be on your calculator. Now, draw a suitable graph. And again, I'm going to draw it here very quickly. So you'll have to draw it on graph paper. I'm going to do it here just for the purposes of ease. Don't have any other way to draw it. And then I'm going to answer the questions. First one. What is the height of the mosquito after 8 seconds? Now, we have to remember here that this is time and this is height along this axis. But here's what I need you to remember. Yeah. 1 unit equals 5 centimeters. Do you remember that? There it is. So every one box up there is actually every one box is 5 centimeters. So 1 would be 5, 20 would be 100, 40 would be 200, and so on. Okay. 40 would be, what did I say, 5 4 is 200, and etc, etc. Okay. So what are we asked? What is the height of the mosquito after 8 seconds? Now, that means you've got to find out where 8 seconds is. Obviously, it's on the time axis. There it is. So what do? I draw from 8 up to the graph like so. So you use a ruler, I can't. And when you hit the graph, you take an immediate right turn, like so. And you notice that it is just below 100. So you could say, for example, that it's 99 units. But the height of 1 unit is 5 centimeters. That's what the question tells me. So I have to multiply that by 5 centimeters, and 99 times 5 is, whoops, sorry, turn on your calculator to comp. So 99 times 5 is 495 centimeters high. So that's the first one. Okay, so just keep in mind that every box that's along the y-axis represents 5 centimeters in height. So 20 would be 100, 200, 300, 400, 500, and so on. Okay. Question 3. The mosquito is caught in the air at a height of 170 centimeters. At what 2 times can this happen? Now, 170 centimeters. That's the actual height. But I've got to remember that every box is 5 centimeters. So I'm going to divide that by 5 in order to see how many boxes I have to climb up to represent that height. So 170 divided by 5 is 34. Now, where's 34? Well, there's 30. There's 35. So it's roughly there. And again, there's y equals 34. So here's what I do. I run across as carefully as I can, and the 2 places that I cut the graph, I drop, like so, and like so. And what are my 2 values? My 2 values are 2.1, 2, 3, 4. So it's 2.24, about 2.5, roughly about 2.5, and here 6.2468, about 6.8 seconds. So what are we dealing with? We're dealing with a height of 170 centimeters, which is, as we said already, 34 units up. Because don't forget, 1 unit is 5 centimeters. So I go up 34 on the y-axis, and then I run across until I cut the graph, drop down, and when I drop down, I simply read the values of the x-axis. Okay, and finally then, verify the answer to 3 by algebra. Now, how do I verify the answer to 3 by algebra? Well, first of all, what I would have to do is to take the function and set it equal to 170. So let me do this by algebra. Let me take off what I don't need. So I'm just going to take this off here, give myself a bit of space to show you what I'm going to do. I need the answers on the graph, so I'm going to leave them there. Take that off. Okay, and that. All right, so let's try the algebraic way. Now, what have we got? Verify the answer to 3. So what's the 3? The height of 170. So that means x cubed minus 7x squared minus 5x plus 75 equals 170. X cubed minus 7x squared minus 5x. Now bring the 170 over. You have to have it equal to 0. So we're going to subtract 170 from both sides. So 75 minus 170, I never take any chances, minus 95. Okay, now with a situation like that, the first thing we've got to do is to try and work out one root, okay? Or you could do the following. You could take your values that are down here and you could try and plug them in and see how accurate they are. All right, that's one way of doing it. But at the same time, we have to use what we're given. Minus 95. So let's just see if 5 is a factor that will work. So 5 cubed minus 7 times 5 squared minus 5 times 5. I don't think it is going to be way too big. Minus 95. Let's just see. Minus 170. No, so 5 is no use to me. Let's try 95 divided by... No, 95 divided by... 95 divided by... There has to be one value that we can get. There has to be one, because remember we told you before there has to be one real value. So 95 divided by 5 is 19. 95 divided by 2.5. Okay, now I'm going to have to stop here. I'm going to try this myself. I haven't got this worked out beforehand. But verify your answer to 3 by algebra. I suppose probably the easiest way to do this, because I was trying to find factors in 95. Here's what I'm going to do. I'm just going to take 2.5 and I'm going to take 6.8 and I'm just going to feed them in here and see what happens. I'm not going to bother looking for the factors. It's going to take too long. So let's just see what we get if I have 2.5 cubed. So 2.5 cubed minus 7 2.5 squared minus 5 by 2.5 minus 95. Now the answer there comes out at exactly what we were looking for. It comes out at 0, very, very close to 0. And I bet you the same thing too will happen with 6.8. So to verify your answer to 3 by algebra, you simply take these values and you feed them into this particular equation and make sure that the answers you get are very, very close to 0. Now what I'll do is I'll work this out and I'll do it on paper and send it to you, because I didn't work it out before I started the video. But what I want you to do, taking all into consideration, is to work on these questions here from page 145, 146 and 147. They're relatively straightforward. Cubic expressions, there's not so much you're going to ask. The majority of our cubic expression and cubic function questions will be ones based on real life. So take these, do them, hold the answers, and we'll come back to them and we will look at them in the next live class.